Hi, today we will be discussing about the central principle of projectile motion. This is an extremely interesting topic in physics, in fact mechanics. And the central principle behind projectile motion, how a projectile behaves under Earth's gravitational field, is actually a very interesting topic. And it was first proposed by the great physicist Galileo Galilei. And we'll take a look at it. Okay. So, first of all, we should address the question, what is a projectile? What actually is a projectile? Is it some sort of contraption which moves in a parabolic path, or is it something which is launched from somewhere? What is a projectile? It's a very significant question, and often you miss out what actually a projectile is. So, take a look at this situation. A boy is throwing a ball under Earth's gravity. So g, I am assuming it to be 10 meter per second square, and he is throwing it at an angle theta from the surface of the Earth. So how will it travel? It travels, we know from experience, in a parabolic path. Assume this is straight. So it travels in a parabolic path. We call the ball a projectile. So anything which travels in a parabolic path is a projectile? No. Suppose you find a bird flapping its wings and is flying through the sky in a parabolic path. Will you call it a projectile? Will you consider the bird a projectile? No. So what is a projectile? A projectile is any body which moves solely under the influence of Earth's gravity. So let me write it here. I want you to take this, understand it word by word, for it is very important. What is a projectile? The answer is, a projectile is any body which moves only under the influence of influence of gravity. Implies the only acceleration acting on the body is acceleration due to gravity. Now this is a very interesting definition because usually you miss out a few cases unless you understand this definition very deeply. Consider a ball which is thrown vertically upwards without any horizontal component. It is thrown vertically upwards. By this definition, it can be considered a projectile. Okay. So anything which is dropped can be considered a projectile because it is moving solely under the influence of gravity, Earth's gravity. Once it leaves your hand, there is no other force acting on it. You ignore air resistance and other pseudo forces, but no other force acting on it other than Earth's gravitational force. So that can be considered a projectile. You throw something horizontal, it can be considered a projectile. So my point is, it need not travel always in a parabolic path. When you throw something upwards vertically, it goes in a straight line, goes up, comes down, same path. Until there is no horizontal component of velocity, it will only travel in a straight path. But it is a projectile. Whereas anything, for example, a bird flapping its wings, traveling in a parabolic path, cannot be considered a projectile. And this is because the wings or the muscles of the bird are working, and they are applying a different kind of force, uh, and that force is acting on the bird. It's not just gravitational force. So acceleration is being created not because of, or not only because of gravity, but also because of muscular forces. So it cannot be considered a projectile. Now, since we have understood what a projectile actually is, we will take up the central principle of projectile motion. These are actually two principles which were discovered by Galileo Galilei through two very interesting experiments. So, as I cannot do the experiment physically here, I will represent it. Okay. So, I will move a bit down. Right. Think of the following. And I think you can try it at home, the first experiment. So, I will say experiment 1. This one you can actually try at home. It's a very interesting experiment and it's actually fun. Okay, you take one ball in one hand and you take another ball in another hand. Okay, you drop the first ball at 0 meter per second velocity and you give the other ball some velocity, say v meter per second, in one direction. Okay, both are released from the same height h. 1 minute, what is this? Yeah, both are released from the same height h from the ground, and the question is, which one strikes the ground first? Pause the video, try to understand the situation. You are dropping one ball and simultaneously, it can be any ball, you can take a pen for instance. You drop one pen, you throw another pen in the horizontal direction at the same time from the same height, and observe which one strikes the ground first. Try this out and continue the video. After 1 2 attempts, it's difficult to do this correctly because you should ensure there is only a horizontal velocity and not a vertical velocity. But if you do it right, you'll find that both of them strike the ground at the same time. Okay, this is something interesting. See, after some time, after say t seconds, both strike the ground. The first one or the second one goes in a parabolic path, as we know from experience, and strikes the ground, and the second one, or the first one, comes down straight, this one, and strikes the ground, and we observe that both take exactly t seconds. Both take the same time to strike the ground. So this is the first principle. This is the first principle Galileo came across while studying projectile motion. It is a very interesting principle. You keep this in mind and problems will become quite simple. Just like that, you will be able to solve problems. So, when you consider a ball being dropped and another ball being projected with a horizontal velocity in any direction, as long as they are projected at the same time from the same height, both will reach the ground at the same time. So both will take the same time duration to reach the ground, which we will call time period. Okay. Now, if you understand this principle, you need not by heart formulas for time period, which you will be studying later in this chapter in motion in 2D. I guess. Yes. So I'll move this out of the way and we'll see. We'll take a look at a question. Okay. So let me change to blue. Consider the following. You are on top of a building. Okay, you are not afraid of heights. Say this is 20 meters. Okay, so this person is not afraid of heights. He is on top of a building and he is throwing a ball. I'll paint the ball like I like cricket, so I'll put it red. Okay, he's throwing a ball with a velocity of say 4 meter per second. 4 meter per second from top of the building, and it hits the bottom after t seconds. Find the time it takes to strike the bottom. This is a very simple question from projectile, which usually we'll be solving using formulas. Usual method. But there again another problem comes. You will understand later. Time is calculated from bottom. Like if the ball had been thrown from the same level and reaches the same ground after some time, you can calculate t using the formula, or you should take the half of the time period, which you will see later in the chapter. But if you understand the central principle, the first principle behind projectile motion, that horizontal velocity is independent. That is, the ball takes same time as long as it is released from the same height at the same instance. It takes the same time to reach the ground. Okay. So if you understand this, we'll solve this using that principle. See, consider, I'm going to show you a small technique. We'll consider a ghost ball. Okay. You consider a ghost ball which is being released from the same height. Consider this to be the same height, and it is being dropped. Okay. The same ball, a ghost ball, is being dropped instead of being thrown at 4 meters per second from the same height. Now let us solve the problem based on this second ball, that is the yellow ball, and find t. Now this is simply motion in one dimension, which is uniformly accelerated. I will consider g to be 10 meter per second square. Okay, throughout I will be considering 10 meter per second square. Okay, so it is being dropped at 0 meter per second. It takes t seconds to reach the bottom. So how will you solve this? How much time it will take? It's simply Galileo's second equation of motion. S is equal to ut plus half at square, one dimensional motion. So S equal to ut plus half at square, right? So the displacement given as 20 is equal to ut. Initial velocity is 0, so ut is cancelled, plus half at square. A is 10, which is the acceleration due to gravity. Half of a is 5, so 20 is equal to 5t square. So solving this, I know you know to divide, so you get t is equal to 2 seconds. See, you solved the problem for a ball being dropped instead of being thrown for 4 meters per second. You solve it for being dropped from the same height at the same instance. You get the time it strikes the ground to be 2 meters per second, 2 seconds. Sorry, 2 seconds. Now, from the first principle, from the experiment you performed, you know that irrespective of the velocity, whether it is being thrown at 10 meters per second, 5 meters per second, 100 meters per second, or 0 meters per second, it will take the same time to reach the ground. So the answer is 2 seconds. So you solved a problem without using any projectile equation, which you will be dealing later in the chapter, based on the first principle. So once you understand these principles, you can solve any problem. Okay. So irrespective of the horizontal velocity, balls take the same time. I am reiterating this because it's a very interesting and important principle, and if you understand this properly, you can solve any problem in projectile motion which comes from this area. Okay. So you can solve simultaneous problems. Now we'll go to a second principle which Galileo himself discovered, which is even more interesting. Okay. So I hope you understood the first principle. Okay. Now let me clear the board. Alright. We'll consider another experiment. Let me make it blue. Experiment 2. Again Galileo performed this, and I am not able to perform this here, so you can try this out, but this is a bit more tricky experiment to perform. It can be difficult. Okay, so you consider a table here. It's a table, so I think I will draw it in 3D. Right. Okay, you consider a table from the ground at a height h, and you consider two balls. But this time, what we are going to do is we will place one ball on top of the table here, and we will place the red ball bottom of the table on the ground, but at the same let's say same horizontal distance. That is, if you consider this to be the x-axis, don't bring coordinate geometry into this, don't complicate it, but Just for your information, both are at the same level. Okay, level in terms of not height but x coordinate. Okay, say this is y and this is x. So x is the same. Okay, y can be different. Both are at different heights. And you give both balls the same velocity. You give both balls the same velocity. Say 4 meter per second. 4 meter per second. And you observe their motion. So what happens is the first ball on top of the table starts moving. Along with it, the bottom ball moves. So this is t equal to 0. At t is equal to say t1. The red ball reaches the edge or end of the table. It is on the earth or on the floor. So it reaches the end of the table, while the yellow ball reaches this end of the table. Both are moving together. Okay, I'll move the red ball a bit so that it matches exactly where the yellow ball is. Okay, because it is moving with the same velocity. So I'll take this to be 4 meter per second. Ignore friction. 4 meter per second. Now what happens? The red ball continues moving. Okay, red ball continues moving, but the yellow ball, having reached the edge of the table, falls off. Okay, now it is falling with a horizontal velocity. So you know this is a projectile. As soon as it leaves the table, normal force ceases to exist. So only gravitational force is pulling it downwards. It is moving only under the influence of gravity. Hence, it can be treated as projectile. Okay, so I'll assume g to be 10 meter per second square. So this ball, yellow ball, drops in a projectile fashion, while the red ball moves straight. Now the question comes, what happens? Will they meet with each other after some time, or will the yellow ball overshoot, or will it undershoot the red ball? This is a difficult experiment to perform because it is difficult to give the same velocity to both balls, but it has been proven, it has been done. Galileo Galilei himself verified this, and the discovery is quite satisfactory. It's quite interesting that both of them reach the same point at the same time. Okay, now how did this happen? Let us analyze this. Okay, both red and yellow balls reach the same point at the same time. At a time t2, in between the fall, you'll find that the yellow ball is here and the red ball is exactly below it. Okay, exactly below. No difference in its x position. Y is changing, but x remains the same. And what do you reckon its horizontal velocity will be? Hmm? It's a very interesting question. You will observe that it is the same, 4 meters per second. But at the same time, v is there, while here it was 0 meters per second. Vertical velocity changed, but horizontal velocity remained the same. And the red ball still continues to move at 4 meters per second without friction. And both are at the same level. See, this is extremely interesting, an extremely interesting principle. It is such a joy to just understand this and adhere to this. See, both are at the same level. Both have the same horizontal velocity. Yellow ball only differs in the vertical velocity and the vertical position, in fact. But both reach the ground or both meet on the ground at the same point at the same time. Okay, we are ignoring friction and other forces, dissipative forces, but the principle remains the same. So what is the principle? What did Galileo Galilei conclude from this experiment? It's a very interesting conclusion. I'll write it here. The vertical motion is independent slash not affected by the horizontal motion or horizontal velocity. I'll write it as motion. Okay, for you to understand. And same is true the other way around. Is it around or round? Other way around. So the principle is horizontal and vertical components act independently. The horizontal velocity does not determine how the ball moves in the vertical fashion, while the vertical velocity does not affect the movement of the ball in the horizontal direction. This is why both of them struck the ground at the same time and both of them struck themselves at the same spot. Okay, so this is a very important principle Galileo himself discovered, and it is a very useful principle in applying for problems. So we will take a look. See, once you understand this, you need not by heart formulas for maximum height and range, because you can solve it using simple Galileo's equations of rectilinear motion. Okay, so you consider this. I'll give you a question and we'll solve from there. See, consider a building again. A person is standing on top of a 45-meter building. He is not at all afraid of heights. He is standing at the edge of the 45-meter building and he is throwing a ball with a velocity of, say, 5 meters per second. Just a minute, let me calculate. Okay, it comes out to be a good answer. Okay, so this is the ground, 45 meters height, and he is throwing a ball at a horizontal velocity of 5 meters per second. The question is, first time we calculated how much time it takes to strike the ground. This time let us calculate how far from the base of the building will the ball strike the ground. Same ball. Let me change the color. Let's not get confused. The same red ball. Question is to calculate the distance between the point of strike and the base of the building, which we call range of the projectile. Okay, so find R, which is the range. Now, if you understood the first and second principles really well, you need not use any formula to calculate this. Or I should say, you need not use any projectile formula to calculate this. You can solve it simply using Galileo's equations of motion. Consider the following. You take two ghost balls here, not one ghost ball, but two ghost balls. One representing the horizontal motion and another representing the vertical motion. We have understood that both work independently and therefore one goes down at 0 meter per second. It is like it is being dropped, and the other moves in a sideways fashion at 5 meter per second. So two ghost balls instead of one. Okay. Now time period. How do you calculate? See, the idea behind solving any physics problem is, first you should have a mind map in your mind. How you will be solving. 2-3 steps. How you will solve. Then start solving. So first of all, my idea is to find the range. I know the velocity. Distance is velocity times time. Horizontal velocity does not change. Okay, does not change. It is throughout constant throughout the motion of the ball. So 5 meter per second remains 5 meter per second anywhere in the journey. Anywhere in the journey of the ball. So as long as horizontal is constant, no acceleration is acting in the horizontal direction. You can say distance is speed into time or velocity into time. So 5 times t. So r is equal to, you can say, 5 times t. Now you should find 5t. How do you find t? T is determined by the vertical component. Okay, vertical velocity is what determines how fast it will strike the ground. Horizontal, it will keep going on. So what determines how much time it takes to strike the ground? Vertical component. So calculate time period from vertical component. It is 0 meter per second. So from s is equal to ut plus half at square, Galileo's second equation of motion, you understand. 45 is equal to 5t square. So I'll write it here. So t 5t square is equal to 45. Cancel this. 9 implies t square is equal to 9. T is equal to 3 seconds. Okay, not plus or minus 3, 3 seconds. So if time is 3 seconds, you can find range easily. Range is here a part of uniform motion. No acceleration in horizontal direction. No accel in horizontal direction. Okay, so range is simply v horizontal times time, which is 3 times 5, 15 meters. This is your answer. See, by understanding the first and second principles Galileo discovered, we are able to solve problems very easily. So the main idea or crux is, number one, independent of horizontal velocity, be the ball or object be dropped or may it be thrown with some velocity or infinite, not infinite velocity, with some huge velocity also, it will reach the ground. The time it takes to reach the ground is the same. That is the first principle. Second principle, horizontal and vertical components act independently. Horizontal velocity is not affected by the vertical component and vertical component is not affected by the horizontal component. So you can solve problems using the idea of host balls. Just break down the situation into two parts, horizontal and vertical. Now you might be wondering, I took only cases where horizontal velocity is alone there, no vertical component of velocity, no vector is there. I'll not be explaining the entire thing now because video will go very long, but the idea is the same. You can work with vectors, split the velocity, like I'll just show an example here. See, this is just a short introduction. This is not the actual lesson on vertical component and horizontal component, but I'll give you an idea. Say it is projected not horizontally. What if there is vertical well as well? Okay, so it is projected at theta with v from, say, again a building. So you can resolve this into two components, v cos theta and v sin theta. Okay, and as soon as you resolve, strike this off. This is no longer needed. So you have created two ghost balls instead of the single ball. You split it into two components, horizontal and vertical. Okay, so the vertical component can be solved independently. Again, you use Galileo's equation, second equation, s is equal to ut plus half at square. Only this time u exists, it is not 0. So you cannot apply 5t square. You can apply ut plus half at square, find t, and then apply it with the horizontal component to find the range or find maximum height. How will you find maximum height? Vertical velocity, when it becomes 0, the projectile is at maximum height. Think about it. You will be able to solve if you understood these two principles. Now what I'll do is, for my satisfaction, I'll give you a small problem to think about. You try to solve this problem and we'll find out that whether you have actually understood this principle well. If not, try to go through this video again. Try to read, I think Rasnik Halday explains this very well. Verma, I think it has a good definition also, but Rasnik Halday is very good in this topic. So just go through it. Ghost balls, resolve them. Treat vertical separately from horizontal. You are done. So consider this question. In this question we have two buildings, not one. I'll give you the principle of the question, you can put in numbers to solve. Okay. So you are throwing one ball with a horizontal velocity. Again, I am only treating horizontal component because I don't want to complicate it with vertical component. To understand the idea, you just need a horizontal component. So I'll give it, say, v meter per second. You can put in numbers, it works. There is gravity, g. Height is given as h. And this too is at some height, h greater than h. Okay. Now you are given that when the ball is projected at v meter per second, it reaches the base. So I'll write when it ball is projected at v, it hits the base. It hits the base. Then if it is projected at u, now when it is projected at v, it hits the base. Now another ball or the same ball is taken up again and it is projected with a velocity u such that it comes and strikes some part of the building here. We are asked to find this height x, or since it is vertical I'll put it as y. Okay, and for simplicity's sake you try to consider both heights to be the same, both buildings to be of the same height h. Okay, when it is projected at u meter per second, find y. It's a very interesting question. Think about it. Try to solve this. If you understood both principles very well, you will be able to solve it without any problem. Pause the video, try to solve this, and I'll give you the solution. Right. The solution is, it's quite simple. I have not put in numbers, but you can do that. Since it is given at, when it is projected at v meter per second, it hits the ground easily. You can calculate time period first for v meter per second to hit the ground, and then using that calculate the distance here. See, calculate this distance between the buildings, x. Okay, using the first case given. Now once you calculate x, you are asked to find y. You already know about x's. You are given u is given some number. So u is given, x is given. You can find the time period the horizontal component takes to cover a distance x, which is x divided by u. Okay, x divided by u is the time taken, and vertical component which is 0. So h is equal to, or y is equal to, in this case, ut, which is 0t plus half into g into the time you found out using x, that is x by v whole square. From that you will get y. So you see, once you understand both principles correctly in the right way, you can solve any projectile question, be it a vertical ball, be it some ball which is thrown at any random angle, be it some ball which is thrown from random height which is not completing its entire course of motion. You can find anything using only two principles, and this is projectile motion simplified. So keep wondering and see you next time.